Who can tell me anything about primes? Yeah.
They're a prime number. They can only be they can only be divided by one in themselves.
That's a recursive
Yes.
definition.
Good.
Yeah, but I'm just clarifying that a prime is a prime number, prime or a prime number.
So the formal definition is that it's an integer greater than 1 whose only divisors are 1 and itself. Okay. Now, prime's really cool for the purpose of competition math. Yeah.
You should extend to the definition that 1 isn't a prime number.
Okay.
Because it's divisible by 1 and itself.
But for whatever reason, we don't consider it to be a prime.
For
Makes
the
sense.
purpose of competition math, prime's really useful because they can help with GCD and LCM and a whole variety of stuff.
Apply it to any other prime.
But for right now, for just number theory, we gotta address FTA. Okay, so fundamental theorem of arithmetic. Does anybody know this off the top of their head?
Jack?
No.
Oh, yikes.
Okay. Basically, it's another basic one, but it's really big. It's basically saying it's talking about prime factorization. Okay. So it's saying that every integer.
Oh, wait, isn't it? I think I know what it is.
Oh, I know this.
I didn't know this was the actual FTA.
Can be written
Is a solid 2 prime.
I think that's in my linear algebra textbook, but it doesn't actually
the
call it
product
fundamental theorem of arithmetic. It just calls it theorem 1.6.
as the unique product. Okay. As the unique product. I apologize.
I literally sent you a picture in the linear algebra quiz that uses this.
What?
The linear algebra had this.
Okay.
I know the theorem.
We're not going to prove the fundamental theorem of arithmetic. There's 2 parts of this proof. One is existence,
Makes sense.
No.
and the second is proving uniqueness. Existence is another wonderful contradiction proof. So, yeah, get excited. Okay, so there's 2 cases, right? We gotta prove that, okay, by existence, I should elaborate on that. I'm saying that every integer can be written as the product of primes. And then for uniqueness, we're gonna prove that all of those products, for every integer, it's unique. No 2 integers, or no one integer has 2 prime factorizations. Every integer has exactly 1 unique prime factorization, okay? Okay, so existence. There's 2 cases for n that we're trying to prime factorize. One is that n is prime, and 2, n is composite. Okay, if n is prime, then it obviously works out. The product is n times itself, so it checks out. Okay. We know that for all prime integers can be have a unique product, or there's existence for the product of, or there's an existence for the prime factorization for all prime numbers, obviously, just n times itself. If n is composite, then that means there exists an n that equals a times b, and a and b are strictly greater than or equal, not greater than or equal to, just greater than or less, greater than 1 and less than n. Can somebody tell me why that's true? Any ideas?
I'm doing 415.
Because it has to be an integer, which is can't be less than 1 therefore.
Sure.
Or has to be a positive integer really, so it can't be less
Okay,
than 1.
positive integer,
And
that's